Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. Today's show continues our TensorFlow Developer Summit series, which I recorded at the event on the Google campus just a few weeks back. The summit was great. I met a bunch of TWiML Talk listeners and friends of the show and got caught up on the new features released as part of the TensorFlow 2.0 alpha. This time around, we're joined by Elena Nieddu, PhD student at Roma Tre University, who presented her team's project in Codice Ratio at the summit. In our conversation, Elena provides an overview of the project, which aims to annotate and transcribe Vatican secret archive documents via machine learning. We discuss the many challenges associated with transcribing this vast archive of handwritten documents, including overcoming the high cost of data annotation. I think you'll agree that her team's approach to that challenge was particularly creative. If you're interested in TensorFlow and deep learning, you'll probably also be interested in the awesome swag box that Google gave to Summit attendees. They included the new Coral Edge TPU device and the SparkFun Edge development board, as well as some other fun goodies. And I'm excited to give you an opportunity to win one with our latest giveaway. To enter, just visit twimlai.com/TF giveaway and let us know what you would do with this kit if you got your hands on it. Of course, we owe a huge thanks to the TensorFlow team for helping us bring you this podcast series and giveaway. With all the great announcements coming out of the TensorFlow Dev Summit, including the 2.0 alpha, you should definitely check out the latest and greatest over at tensorflow.org, where you can also download and start building with the framework. And now, on to the show. All right, everyone, I am here with Elena Nieddu. Elena is a PhD student at Roma Tre University, and we're together at the TensorFlow Developer Summit where she gave a talk yesterday. Elena, welcome to This Week in Machine Learning and AI.
Thank you, Sam.
Awesome. I'm really looking forward to diving into this conversation with you. I had a chance to catch your presentation yesterday, which was about the project you worked on in Codice Ratio.
Yes, in Codice Ratio.
In Codice Ratio. My Italian is very rusty.
It doesn't matter. It's actually Latin, so.
Okay. So my Latin is non-existent. Non-existent at all. We'll be diving into that, but to kind of get us started, I'd really love to hear about your background and what got you interested in starting to work in machine learning and AI.
I began working with machine learning exactly when I started working at the project, because I have studied computer science at university. But I was more like operations-oriented, systems-oriented, and very much I didn't think I would join a PhD or something like that. But then when I was searching for a thesis, for my master thesis, then this project came up. And it was very interesting to me because since it's about applying machine learning to the context of historical documents, and I had somewhat a background in classical studies in high school, then it seemed to me like it was the perfect match for me, like because it joined two of my passions, two of my interests. And also it might have been for me the very last chance, or so I thought, to learn something about machine learning, because then I suppose I was supposed to go work somewhere. And then I just said to me, well, let's give it a shot.
Okay, awesome. So the project that you're working on, describe the project for us. What's the ultimate challenge?
So we're used to think of big data as something that happens in the web. So very large amounts of data we produce every day. It's talk every one of us has heard at least one time in their life. But something that we sometimes fail to consider is that there is lots of historical precious information that is stored in physical archives, like in literal paper and something like that. And in Rome and in the whole of Italy and the whole of the world, really, there is lots of huge archives that mostly are still undiscovered because of their size and because they're physical, they're not on a web. And so the goal of the Codice Ratio project is to make these archives accessible. And in particular, the Vatican, we're working on manuscripts inside of a Vatican secret archive. Now,
I feel like if it's called the secret archive, we shouldn't be working on these.
No, this is. I'm glad you're saying this because this is a common misconception even with Italians.
Okay.
Because the secret in Vatican Secret Archive does not stand for confidential, but it comes from the Latin origin of the word secretum.
Okay.
Which does not mean confidential, it rather means private or separate, because the Vatican Secret Archive is a private property of the Pope.
Okay.
So each Pope inherits the archive, that is the center of all the administration, of all the archived administration of the Church.
So the challenge is to do what with the documents in this archive?
The leader of the project, Professor Marialdo, who is also my PhD advisor, he's an expert in knowledge extraction from web sources. And so the project precisely started because he was wondering whether we could apply the same techniques to the domain of historical documents. And so, the goal would be to build a knowledge base, a historical knowledge base out of the documents. But the very first challenge you're facing when you want to do that is that most of these documents aren't digitized, and if they are digitized, they're digitized as images, they're scans. And for those that are printed, you can use traditional OCR, and then it usually just works. But then there is more ancient documents that pre-exist the invention of the printing press, for example, and they are by necessity handwritten. And so that's where the classical OCR fails, and you have to think of something more smarter, I guess, or it's a greater challenge than simple OCR.
Mm-hmm. And so was this project already in existence and ongoing when you joined it, or?
It was starting.
Okay.
I was actually dragged into the project because one friend of mine had already done his master thesis, and he was the very first person to begin the code base of Codice Ratio.
Okay.
Ciao, Andrea. And he told me, look, this project is great, you should join it. And so it was just starting. And then I followed up on his work. But it was about 2 years ago now. Mm-hmm. And the project had started for like 6 months or so.
And so to provide some context on the size of the secret but not secret archive, I've seen a couple of comparisons, one to the Panama Canal, the other to Mount Everest.
Yes.
What are those?
Well, that's to give a hint of the scale, and that's like Professor Maiorino, who works at the Vatican Secret Archive. He likes to say that if we were to take each shelving of a Vatican Secret Archive and put it one next to the other, we could cover the length of the Panama Canal. It's 85 kilometers of linear shelving. Mm. So it's a very large collection. It's a very varied collection. Like you have documents from China, from Asia in general, from Europe, from the Americas, and Africa, and so on. And they span centuries. Like there is documents as old as the 9th century.
Okay.
And up to this day, really, because the archive is still active. They are still collecting documents that other institutions inside of the Holy See don't need anymore, because that's how it works. For example, suppose there is a chancery somewhere in the world that belongs to the Holy See, and when they have to archive their files because they are not using them anymore, they send them to the Vatican Secret Archive. So not only it's 85 kilometers, it's growing.
Okay. Interesting. And so is this project focused on a particular subset of the documents, or are you kind of randomly picking them, or?
Right now, we're focusing on medieval manuscripts.
Okay.
Which
sounds like a pretty broad subset.
Yes, it's still a pretty broad subset, but it allows for some consistency. Mm-hmm. And in particular, we're working on a collection that is called the Vatican Registers.
Okay.
The Vatican Registers, they record every letter that the Pope sent in an official way. So every time the Pope was to send a letter, of course, he would write it. And before it was sent, it was copied inside of the Vatican Registers, so that there was a proof that that letter was sent, and also people could read it if they needed to, because before there was canon law, what the Pope actually said in letters was the law, acted as law itself. And so it was important to scholars, to law scholars back then, like in the Middle Ages. Mm-hmm. And that's a subset of documents we're working with, but our goal is not just to transcribe that, but to create a methodology and to create a way so that if tomorrow we were to change documents, the documents we're focusing on, we could just reapply the same techniques and get similar results.
So you said that this project was really your first introduction to machine learning, and also the project was just getting started as you joined it. It sounds like a lot to figure out for someone new to machine learning. Maybe can you share a little bit about how you got started and how the project has evolved?
As I mentioned, the project didn't start necessarily as a machine learning project. It started as a knowledge discovery project in general. And transcription, in the beginning, transcription wasn't even the main focus. Okay. They thought that since OCR is a solved problem, well, we will just OCR the documents and then we'll see. And then we found out that was just not the case, and we needed something that was smart, that helped us really transcribe what was there, because it was not trivial at all. And in the beginning, what we did was we went to experts in reading ancient writing. They're called paleographers, and we asked them, like, do you think this is possible? And they were like, no way. I have studied years to do that. No way a computer can do that. And then the second problem was that we were searching for how other people solved our own problem, because we didn't think we were the first to find this kind of issue. And what we found out is that many systems that work also very well, but they require a massive amount of annotations. So, for example, say you want to have a good transcription for a page, then you have to provide like at least 1,000, 3,000, 10,000 lines carefully annotated. And since this kind of writing can be very hard to read, even when paleographers know of these tools, they get very discouraged, because they say, okay, it's not cost effective for me. Why do I have to give you like 1,000 lines? That is months of my work, even years, if it's very hard to do, just to have a transcription of a particular document. It's not scalable. So the first thing we found out, it was that the main issue was scalability. And so that's one of our greatest concerns.
And so what is an example of one of these more classical techniques that requires that much annotation? And is it the same kind of annotation that we do on the machine learning type of a context?
Yes, but usually you can use unskilled workers to do that. For example, you put work on Amazon Mechanical Turk, Crowdflower, or you name it. It's usually easy tasks. For example, the one that you're solving when you're doing CAPTCHAs. So like mark the boxes that have stop signs in it, or mark the boxes that have pedestrian crossing or something like that. And then it's easy and everybody can solve it because it's trivial. Or is there a cat in here? Yes, no. But when we're looking these kind of manuscripts, like I said, you need an expert. And experts are expensive, both in the literal sense, that's time-wise, because you need time to get it done. And there is people who do that, For example, there is the read project. They allow you, if you send them enough annotation, they will train their own system and let you have the transcription for following parts and then iteratively improve on that. But even when we talked about that with paleographers, they told us, yes, we know of that system, but we just don't use it because sometimes it's not worth our time. We will just do it ourselves if that's the amount of work we're supposed to do. So I don't mean to say it's not useful, because it can be useful, for example, for the end goal of transcribing entire collections, but you have to be invested in doing that. And more often than not, maybe historians are focused on finding a particular occurrence, and they don't want all the rest of the hassle.
And so in this project, what I'm imagining, one of the big challenges is still annotations and having some kind of labeled data set.
Yes. How
did you go about that?
I feel it's a challenge for many machine learning practitioners because, of course, when it's about business data, maybe you're an industry and you already have that data and you just have it's there and you just have to use it. But for many other fields, and especially in the humanities, there is no such thing. And so what we decided to do was not to annotate by line or by word, but to annotate single characters, because of course the size of the alphabet is way smaller than the size of the vocabulary, and also it suffers way less of the skew of the distribution. What I mean by that is that if you consider the whole 100 pages of text, it could be Latin, but it could also be English. What you will find out is that there is a very few words that occur an enormous amount of times. Mm-hmm. And then most of the words, they just occur 10 to 30 times. And they are the same words you would be more interested in recognizing, because maybe there are verbs, they are names, and so on. You don't care about conjunctions or the, and so on. And that is why the systems require lots of data. Okay. Because you need a good amount of each relevant example.
But letters, on the other hand, are more distributed.
Yeah, letters are more even distributed. Of course, for example, vowel in Italian and Latin as well, vowels will occur more frequently than consonants. But still, it's something you can get over with. And so that's what we... And also that enabled us to create a system that was very much like the CAPTCHA solving system. Mm-hmm. So we made our own custom crowdsourcing platform, where the workers were shown an image of a word, and then on the upper side they were shown some positive examples of symbols that they were supposed to recognize inside of that word, without even having knowledge of the symbol they were searching for. And then they were asked to mark by clicking inside of the image the areas that corresponded to the example they were provided.
And one question that I had was, were they annotating on a letter-by-letter basis or a stroke or subset of a letter basis? Okay. I thought I saw something that suggested it was done at the stroke level and then you were combining strokes to form letters.
Yes, of course. Since we couldn't know before which parts of the word would correspond to which letter, because otherwise we would already have transcription by definition. Then we use a system that can over-segment a word in its strokes. So, for example, maybe you have an M, and the system will segment it into 3 sticks. And so if workers were asked to mark an M, they would just click on the 3 sticks and then submit their answer. A bit like what you do when you have an image segmented into small squares, and you click on the squares. Pretty much the same principle, a bit more fine grade.
And so in this case, you created this labeling interface, and as opposed to using our mechanical turkeys, you used what? Resource.
In Italy, it's not that easy to access to Mechanical Turk or crowdsourcing platform in general. And also, high school students have to work a certain amount of time in the last 3 years of their high school. And so they join projects where they are supposed to do works that are related to their kind of studies. For example, high school students, like I was myself in classical studies, maybe they will go to museum and help tourists or something like that. Or those that are more science-oriented, they might go somewhere else or to laboratories or industry, something like that. And so thanks to high school teacher Marika Shone, we were able to present our project, our crowdsourcing platform, as a working platform for high school students. And also, they were given a few lessons about image processing, machine learning, and also paleography. And they were able to visit the university. Sometimes they worked for us at the university, at our labs. But the good thing about that was that they could also work from home. And so they were very flexible on when and how to work, and that was an advantage that also the professors, their teachers liked, because sometimes to do the work part, you have to skip the school part. And so, of course, teachers are not very happy about that. And in that way, they could manage their own time.
Okay.
And see a different way of working in some way.
So you have these crowdsourced annotations that you collected from the high school students. How many, or what was the volume of annotations?
The annotations, there are more than 40,000 annotations over about 30 classes. 30
okay, so the
classes.
30 classes are letters approximately.
Yes.
And so you have 40,000 examples of letters.
Yes, of course, not by character. We have about, depending on distribution of the characters, but we have about 1,500 examples per character. So that's where the 40,000 comes from.
Often when you're working with crowdsourced data, you'll do things like you'll have multiple workers annotate the same thing and do quorums or things like that. Did you do anything like that, or was there a higher level of trust that you'd established with this group that allowed you to skip that kind of thing?
We experimented with different levels of, we just had a threshold. So, for example, we considered good things that were voted more than 3 times.
Okay.
Or 5 times. We experimented with different thresholds. And, or for example, we realized that some characters were more challenging than others, and we didn't want the students to spend too much time on too easy characters, but or maybe there were characters that occurred less. And so in the case of characters that occurred less, maybe the threshold was lower. Or characters that were very easy, that we saw the student didn't get them wrong so often. And in some other cases, it was not as clear. Maybe it was harder for them to find them inside of a word and so on, and then, so the threshold was higher.
And so you collected this training data, presumably to train some kind of model. What kind of model did you train, and how did you arrive at that model?
So we, in the end, settled for a convolutional neural network, which is pretty standard considering image processing tasks. But we wanted to build incrementally, because we didn't want to we could have just downloaded one big model, but we knew our dataset wasn't that big, and it wasn't as hard as ImageNet. Okay, recognizing single characters is more like NIST than it is ImageNet. But at the same time, we wanted something that really fitted our data. So we just started simple, very basic logistic regression, and then improved from that to see at each step how better we were doing and why.
And so when you say at each step, meaning at each kind of iteration of the modeling step, or?
Yes, we would go about a cycle of, for example, first of all, choosing a type of network of architecture in general, and then seeing just as it was, seeing how good it did, and then, for example, trying to change hyperparameters inside of that model, and then we would try to make it more complex. So, for example, if it was a feed-forward network, then we would just start easy 1-2 layers, and then tune the hyperparameter inside of those, and then when we were sure that we couldn't get better, we would choose the best configuration and then maybe add a layer, remove a layer, and see, for example, because there is a at some point you won't improve anymore because the model has limitations, and so we did that for a certain number of times. So starting with the feed forward and then moving to convolutional.
And we're here at the TensorFlow event. Presumably, you're using TensorFlow to do all of this. What was that experience like?
Well, it could be challenging because there were so many things, so many ways you could do the same thing, and no one was necessarily better than the other. Mm-hmm. And for a beginner, that can be like a bit scary. But of course, I wasn't alone because I was a beginner, but there was somebody who was not, that also directed the whole process of building the network. That was Simone Scardapane, who is also a Google developer expert in machine learning. And so we were together in this, and I was guided. Like, I didn't do it all by myself. Of course, I did my fair share of studying, of working on it. But
so which APIs did you use for?
Okay, so the thing is, for example, we were very torn apart between Keras, and pure TensorFlow, because we loved Keras for prototyping because it kept the code small and very readable, understandable, much object-like, something you would like, you're familiar with, maybe more familiar than other approaches. But then at some point, for example, maybe TensorFlow had a new feature and Keras had to implement it inside of, and it was constantly lagging behind. And so, before the integration at least. And so, or maybe they said, we're now supporting a TensorBoard. And then, for example, it was true, but it was true only for a very restricted set of operations. Okay. And so, since we sort of wanted to have it all, and so, and so maybe sometimes we would just, for example, prototype fast in Keras, and then when we were pretty sure about the model that it wouldn't change much anymore, we would move to pure TensorFlow.
Okay. And was that process difficult or just tedious?
Well, at some point, like TensorFlow introduces the high-level API layers, and so it was pretty much straightforward because it was one-to-one. Like syntax changed a little bit, but not so much. But of course, it was a hassle. Like you constantly have to do back and forth. So the last model we trained, the one that we are using right now, but we're trying to improve on, but so far, was implemented in layers and estimators. It was actually implemented in layers and estimators so that we could take full advantage of TensorBoard. And for example, at some point, we wanted to try the deep dream technique to generate images at each layer of the network to understand what was learned. Right. And we just couldn't do that in Keras.
Because it hid too much of the internals from you. And so this model, you've got this CNN that's basically classifying these characters within the words within these documents. What's the broader kind of pipeline that fits into?
Okay. Of course, since we have this, we recognize that recognizing character is a limitation because, of course, then you have to provide the network with characters. So there is a whole image processing step before the actual classification so that we can provide the network with actual characters. Or maybe not, and because that's the point. When you get to a word, it's pretty easy to segment into words. Then you get to a word, and then everything is written all together. It's very it's cursive script. So each character starts when the other ends. And it can be very tricky to understand where character starts and where a character ends. So we have a few like old school computer vision heuristics that help us cut these whole words into subshapes, or like if they were puzzle pieces in a way. And then we combine these puzzle pieces together. Like we make the network classify them in isolation and in combination. So and then the networks like has some confidence on those classification, and can also has a special class that's supposed to represent a wrong segmentation. And so the network can both tell you, according to my knowledge, this is an A, or it can tell you, no, that's not a character, drop it. So that helps us prune the whole space of the possibility, which otherwise would be like very large, because we're constantly combining adjacent pieces of the puzzle that are parts of the word.
Is it like is the segmentation is kind of like a sliding window kind of thing, or is it more the algorithm is producing distinct segments, but it's noisy?
Yeah, more like the second one.
Okay.
In the beginning, we used the sliding window, but it produced way too much noise.
Yeah.
And then you're very dependent on, for example, the stride you're moving at. So,
right.
And you may have noise from other characters in the background, on the sides, and so we have this heuristic that basically computes the higher contour and the lower contour of the characters, and wherever there is a local minimum or a local maximum, because that's how the handwriting goes.
Yeah. Oh, that's interesting.
And then we're able to connect them, and we create strokes from the characters. So each segment could be either an entire character or a part of a character.
So then you have these, you kind of pass through the first step in this pipeline is passing through the segmentation step.
Yes.
And then for each of these segments, you're passing it on to your CNN to tell you, is it, which of the 30 characters is it, or is it not a character?
Exactly. And then at this point, you still may have some ambiguity, because, for example, there is things you might not be able to solve. Consider, this looks so much better if I can draw, but but okay, consider when you have, for example, one word we often use as an example. Let's try and make this imagination challenge. Okay, is anno, A-N-N-O. Now, in this handwriting, the I's have no dots on them. Okay. So even though, so you broke anno into pieces with our segmentation, and so probably what you will get is A and then a series of sticks, because they could either be I's or N's or M's. Okay. And then you get the O. But then again, for example, each of the sticks of the N's could be either I's, they could be all from the perspective of character recognition without having further context. They could either be I's, they could be N's, they could be M's combined with I's. And all of these combinations are valid from the point of view of optical recognition of the visual features. But then again, of course, only one of them is correct, which is the double N. And so to know that, you need more context, and that context is the knowledge of the Latin language. So that is why even though we have classification, then we need to rank. We could have ambiguity on some words, and so we have to rank them, and we rank them according to a language model we build out of Latin texts. Okay. So of course, the language model picks the one that sounds more Latin-ish.
From your classifier, you produce kind of a list of the top N candidates. Yes. And then you pass that to your language model to basically reorder, re-rank them based on the semantics or the context of the language.
Exactly.
And then that gives you your transcription, your transcribed word.
Yes.
Right?
it gives us a ranking of transcriptions, and so the metrics we're using are not just correct or not correct, but also how good were they ranked.
On that note, how do you kind of evaluate the performance of the network?
So of course, we evaluate the performance of the network on the single character recognition, but also we evaluate the performance of the pipeline as a whole at word level. So the network by itself has 94% average accuracy over 33 classes. But then, of course, since there is ambiguity, or maybe sometimes the segmentation can go wrong, or since it's a very pipeline process, at each step you could introduce error, or also the network might be wrong. If the segmentation were perfect, so for example, if we didn't have that kind of ambiguity, we could get up to 80%, 85% accuracy. What we actually have is about 65% perfect transcription, and then we get up to 80% if we consider minor spelling errors.
Okay.
So for example, maybe an E was mistaken for a C, or sometimes, since convolutional neural networks are terrible at counting, you have like a double C or a double S, and so double letters, which occur pretty often, they might be conflated into one single letter. Okay. So it sees like two S, and then it just say one S, because it's twice the same symbol, but it's just, it's when you have an image of cat, you want the classic network that tells you cat or dog, and it doesn't matter how many cats or dogs are in the picture. It will not tell you it's not a cat if there is two cats.
So the language model is only really ranking the candidates that you give it. It's not doing it can't do anything like, it's not like an embedding that's looking at possible words around the ones that you give it that would be more likely, so as to like correct for these single letter spelling errors.
Okay, so far we experimented with error correction, but only in the form of Viterbi, like
of what?
A hidden Markov models, something like that. And so using the Viterbi algorithm. But the problem we have with that is that sometimes it produces more candidate transcription and more noise. Okay. And so maybe we can get a few words corrected, but then we greatly, our ranking gets worse because there is so many things, there is more things that it has to consider. Okay. And the more alternatives you produce, the more likely it is they sound like Latin. And so that language model would put them like on top, even though maybe they weren't correct. So you mentioned that the character classifier is performing at like 94%, the pipeline at 64 or 80, depending on whether you're counting these spelling errors. How does that compare to the paleographers and their performance? Well, of course, you would have the ground truth we're testing against was written by paleographers, so you have to assume that they are 100%. So that's the limit. We do not expect, of course, to do better. Even though sometimes it actually occurred that maybe paleographers made a very small spelling error, especially when they were dealing with many sticks. Because suppose you have like U, M, N, I, U, and etc. That's very, very common sequences that can occur. Consider like numerous. It's like it's all sticks, and sometimes they get the wrong count. Okay. And so they also may get it wrong, and sometimes it happens. But it's like, I guess they get 5% wrong, maybe. Okay. At most. Maybe to kind of wrap things up, what do you plan for the future with this project? What are the next steps? Okay, so of course we have collected some more data since then, but always at character level. Just it changed the way we did it, so that it enabled us to keep to be aware of the context characters were put in. And so one very first step I would like to go into is trying to create a system that both performs segmentation and recognition. So we have done recently a few tests, and it turns out that this part of handmade segmentation is one of the major bottlenecks we have. So right now we depend highly on how good we can do with the segmentation, and so maybe to train a segmentator could be interesting, and see what happens. Maybe it doesn't work, but it's worth a try. And then of course our end goal is to move to sequence models. Because there is things that otherwise we wouldn't be able to solve.
Like
that
LSTMs, RNNs, that kind of thing?
Yes, exactly. Or anyways, for example, models that use attention, I don't know, like the captioning ones.
Okay.
To see the problem of transcription as one of captioning somehow.
Okay. Oh, interesting. Yeah.
But for that, of course, you need the line dataset. And our focus is on scalability, and that's why we would like to try generative models to help us improve the dataset that we have. So, for example, we are able to reconstruct words from the annotation of the students. They are a bit noisy, but they still look pretty good, like they look like words. And then if we were able to feed like a generative model and to explore latent space and create slightly different versions of the same words, so that we could augment our dataset. So,
okay.
And
the character dataset.
Combining the character dataset into creating words,
okay.
and then augmenting those words.
Oh, okay.
And so creating very realistic synthetic dataset. So as always, you could get a paleographer to do that, but we want to involve them just what we like in the. As always, you could ask an expert to do that, but where our concern is scalability. So we want to be as unsupervised as possible in this.
Is part of this, the way this could play out, is you have the model that does it at the character level and kind of gets good enough at that you can generate some transcriptions, and then you can use those to train the line level model?
Exactly.
Okay.
Or maybe integrate, so maybe we generate some transcriptions, and then so the paleographer just have to say, okay, this is wrong, but this is right, and then a bit like translator do right now with Google Translate. So they give it to Google Translate, it does a so-and-so translation, and then they just correct it, and they go faster this way.
Any advice for folks that are kind of embarking on projects like this, or just getting started and?
Well, just don't be scared, because you can do it, and it's don't expect yourself to be able to do that in one day, but eventually, like going step by step. And it's at some point, like if somebody asked me, where will you be 1 year from now, 1 year ago? And I wouldn't answer, I would be here. So.
Right. Awesome. Well, Elena, thank you so much.
Thank you.
All right, everyone, that's our show for today. For more information on Elena or any of the topics covered in this episode, visit twimlai.com/talk/243. As always, thanks so much for listening, and catch you next time.